Hi everyone, and welcome to another workbook walkthrough. In this video, we will be reviewing the workbook on linear modeling and the three most relevant to us types of regression, namely simple linear regression, multiple linear regression, and our first step into machine learning, logistic regression. Let's get started. All right, so we are working with loading our libraries just like last time. This time around, we're going to use the following libraries: scipy.stats, which is all sorts of statistical functions that could potentially be useful. You can click on this link, open it in a new tab, and then you will be able to see what scipy.stats is all about. The same thing with stats models, which is the typical Python statistics package. OLS, which we will need for regression. It's the ordinary least squares function within stats models. And of course, as previously, scikit-learn. And we've already seen this package before. In order to really experience what regression has to offer us, we're going to use a different data set this time. It's called the insurance prediction data set. We have two forms of this data set. The first one is the original with numeric and categorical attributes that are mixed. That is this one here: age, sex, BMI, children, smoker, region, and charges. We are seeing here for region, for example, southwest, southeast, and so on. We have a second version of this same data set in which the categorical data is converted to numerics. That's what we're seeing here. It's under this link. So we're seeing here, instead of region, southeast, southwest, etc., we're seeing 3, 2, 2, 1, 1, 2, and so on. So this is the data that we're going to be working with. Back to our workbook. We're going to first import our libraries. Note here, we're going to use our OLS as announced previously from statsmodels.formula. And we're also going to use scikit-learn, the linear model specifically, and we're going to use, just so that I can embed videos and images, our IPython libraries, HTML and image again. So now we're going to read in the data into our insurance data frame. And then we're going to verify that we can see the data. All right, and here they are. So this is, in fact, the categorical data set, or the data set that contains the categorical data. That's what we're looking at here. All right, so now let's verify that all data types have been imported correctly with insurance.dtypes. And we're seeing here age is an int64. That's good news. Sex is an object, which means it is categorical. BMI is float. 4, because it has a decimal point here. Children is an int again. Smoker, we expect to see as object the same as region. And then the charges, of course, again, here are a float 64. So it looks like all of our data has been imported as intended. So let's get started with our exploratory data analysis. The first thing we're going to see is how the independent numeric variables relate to our class attribute. Now, in our case here, the class attribute is charges, because our charges depend on how old the person is, what sex the person is, what their BMI is, whether they have children, whether they smoke, and where they are located. So charges is our class attribute, or a dependent attribute. So let's see how age relates to charges, for example. We're going to use a scatter plot to do that. Interesting. So we're seeing 3 bands here, right? We've got a solid band at the bottom here, and we have a somewhat less solid band here and here, and then we have, we have this here, which is really interesting, but what we can see is a tendency. And the tendency is that the older a person gets here, right, the higher the insurance charges are. So that's the number of claims. That's the money that the insurance has to pay for the person. So we're seeing a few outliers here, of course, right here. At the age of 30, 31 something, right? We're seeing an outlier here at the age of 45, but still those are outliers. The majority here is what we're seeing as a trend that is climbing. So, okay, good. Age versus charges. Let's take a look at BMI versus charges. Same thing. Interesting. So what we're seeing here is this blob, and then we're seeing a little bit of this. Let's see. So the higher the BMI gets, we can't really say that the higher the BMI gets, the higher the charges get in all cases. Now we have this blob here that would indicate that, yeah, we have people with a higher BMI who have incurred higher charges. But that's not true for everybody with a higher BMI. So now the next step will be to look at the correlations between the attributes. Let's take a look at our numeric only correlations between age, BMI, children, and charges. And what we're seeing here is that the correlation coefficient between age and charges is at 0.299, so really much higher than the correlation coefficient between BMI and charges. And that makes sense when we look at these two different scatter plots. Again, here's BMI versus charges, and here is age versus charges. We see a much stronger correlation here than here. And there you have it. Of course, I'm going to ask you in the first your turn to display just the attribute below here that has the highest correlation, the best correlation to charges, and we just discussed that. The next thing is take a look at how the number of children is connected to charges. Does having more children mean higher charges? Now go ahead, build the scatter plot, and take a look at the relationship. And then let's think about it. What if we could find an actual rule that could connect the variables? And this is where regression comes in. Regression helps us relate the independent variables in our data set to the dependent variable in our data set, that is, to our class attribute, with the help of a formula. This means that if we have a formula, or when we have a formula, we will be able to predict the values of our dependent attribute if we use values for our independent attribute, and that is our goal. We're going to start with the simple linear regression that works with just one independent attribute. The formula for that is y equals f of x plus b. X here is our independent attribute, y is the dependent attribute. And we have our coefficient b here. Our coefficient b is the value of y if f of x evaluates to 0. So that is, in fact, the place at which, if you want to speak about it in graphical terms, our graph crosses the y-axis at x equals 0. So how does simple linear regression work? That is a long story, and there's a great explanation in this video here. All right, so now that you know about ordinary least squares, we're going to use them in order to establish the parameters in our regression model and minimize the sum of the squared residuals. So we're going to use our formula here. Our output will be shown as y equals f of x plus b. And we're going to make sure that the calculation considers our constant b, right? So this is why we use add constant below. And otherwise, all we would get is the coefficient f as our output. So here we're going to set our x, that's our independent variable, as age. Our y is charges. And then our x, here we're going to use from stats models here the add constant for x, and that is this b, right? So now for our first model here, insurance.mod1, we're going to use OLS of y, that's charges, given x, age, and we're going to fit this model right away, which means we're going to apply the model, right? And then we're going to display the model summary here. Let's do that. Whoa, that's a lot. Let's see. This is what an OLS regression result looks like. So where do we get started? Well, it's a lot to take in, but the most important part is right here in the middle, and we're going to talk about that. This is where we see our coefficients, right? We're seeing our coefficients, we're seeing our standard error, we're seeing our t-value, we're seeing our p-value here, which we already know from before. If a p-value is small, that means our results are statistically significant, right? And we're seeing these values here as well. We'll talk about those in a little bit. So the most important thing here is the coefficients. So we can say that if we multiply our age by 257.7226 and we add 3065.885, that is when we get our charges. So our formula y equals f of x plus b will look like y equals f of x. F is 275 times 7226 times x plus 3165.885. So this means that if age increases by 1, the predicted value of the charges increases by 257.7226 plus 3165.885. All right, so let's go back. We've taken a look at the middle here. Now let's take a look at the top here and see what we can learn from that. So we know that the dependent variable is charges. We've used ordinary least squares here. All right, so the next thing that's really interesting is, of course, our number of observations. We are looking at 1,338 data points. We're looking at two attributes, namely age and charges. So this means that our residuals are going to be 1336 because it's 1338 minus 1, 2, and that is 1336. Okay, good. So for the residuals, we have that. The next really, really important part is the r squared and the adjusted r squared. We're not going to worry about the difference between the two at this point, but what is interesting is the r squared value. The r squared value describes to us the percentage of the data that can be explained through this formula that we've just found or through this model. So in other words, here, if 1 is 100%, that means that 8.9% of variations in charges can be explained through this model. Now that is really not very much. We would like to see an R-squared value that's much higher, because that would allow us to have more confidence in our model that we just found, but the data don't bear this model out. More information is right here, and here's another great video that will allow you to understand exactly the details of the regression output. Okay, so let's take a look at these numbers again. We're going to print the parameters here, and especially the R-squared value, and 8.9%. Let's compare that with the graph. So the graph is up here, and what we thought was a pretty clear, positive correlation really turns out to be not as stringent as we thought it would be, because we can explain only 8.9% of this model with our formula. Okay. That's not exactly fantastic, right? Let's see if we can, what the y hat looks like. That's the predictions here. So, okay, here we have the calculated values. So now let's take a look at the regression plots themselves. And we can see the residuals versus age. Remember, when we look at residuals, we would expect them to center around 0. And what we're seeing here is it's pretty clear that the residuals do not center around 0. Then we see here the y and the fitted y versus x here. And that trend is pretty clear. So we see our y hat bears things out, but we see there's a lot of data above our y hat here. And that's what we're seeing with our regression plot. And we're basically just duplicating this red line down here as the black line. That's our best fit line, our regression line, right? And we have the same results. So yeah, maybe not so good. Let's see if we can improve on these results. What if, instead of using just one attribute, namely age, in order to predict charges, we could actually combine the values of a number of numeric variables to predict the charges? Maybe that will give us a higher R-squared value and a better, more reliable regression formula for that. That's where multiple linear regression comes in. Multiple linear regression is just like simple linear regression, only that we take not just one attribute in order to predict our charges, but we use a number of them. So in our case here, let's scroll up to our correlation table, which we need for this. We see that age is, of course, the best predictor with a 0.299 correlation coefficient, followed by BMI. And we've seen in the graphic that we had on our screen beforehand that BMI is really not that super fantastic. And we have children as well. Well, what would happen if we used, instead of just age to predict charges, if we used all three here, age, BMI, and children? Let's do that next. So, multiple regression. The formula is basically identical to our simple linear regression formula, only that we're using not just age, but also BMI and children. And our Y is insurance again, charges. And then let's see what our, here we go, our X variable is. And then we're going to set up our linear model here for the linear regression. And we're going to, again, fit our X and Y. And then let's take, instead of displaying the entire output, let's look at just our R-squared value. And look at that, our R squared value has increased. That's exactly what we wanted. It went from 0.089 to 0.12. So now we can say that we can explain 12% of our value for charges by using age, BMI, and children as the input. Okay, not much better, but better, right? Let's take a look at the coefficients for these predictors here, and we're seeing age, BMI, and charges. Okay, and then let's take a look at our constant, at our B, which is also called the intercept, because it intercepts the y-axis when our value for x, remember, is 0. And this is our intercept, which is negative, doesn't matter. So our formula for the multiple regression, instead of the simple regression, would be now 239 times 0.99 times age plus 332.08 times BMI plus 542.86 times the number of children minus, because this is negative here, right, 6916.24. Good. All right. Well, let's see. There's got to be a better way and a more reliable way. We have already increased our R squared value from 0.089 to 0.12. That's 12%. But let's see if we can do even better. For that, we're going to use all attributes. Because remember, we have more attributes in the data set. We have, if you do insurance.info, you'll see them. We have age, sex, and BMI. Okay, good. Children, smoker, region, and charges. But we haven't looked at sex and smoker and region yet, right? So let's take a look at that. So first we're going to set up our X and Y attributes again. There you go. We're going to print X and we're printing Y here at the bottom. And now we can run our multiple regression again. But this time we're going to use a process called backward elimination. So backward elimination means we are using, for our full model, all of the variables here, all of them, in order to get our first result, and then we're going to remove the least significant variable. And how we're going to predict significance, we'll see in a moment, right? And then we're going to remove the least significant variables until we reach a stopping point that will optimize our R squared value. And that is, our stopping rule is we want to find the highest R squared value. Okay. Wait, there's one snag though, because we're seeing here, of course, that we have categorical values, right? We've got sex is an object, smoker, and region are objects too. So this means we're going to first need to translate those into numbers, right? We need to make those numeric. I've already done that in this case. This would be a step you would have to undertake if you didn't have the Insurance 2 data set, which is this one in which our categorical attributes have already been translated into numerics. Remember, this is the original data set. This is the one with the translated values. All right, so let's load that in order to make things a little bit shorter. We're seeing here that sex has been translated into on and off 0, 1. Children has been is original. Smoker has been translated into 1 and 0. Region, we have 4 different regions. That's what we've seen before. So the region has been translated into a numeral as well. And there's one additional column that I've added to this, is insurance claim 1 and 0. 1 means yes, an insurance claim has been made, and 0 is no insurance claim has not been made. However, we're going to, for our purposes right now, delete this column. We're going to use it later when we talk about logistic regression. This is when this becomes important. So first we're going to delete our insurance claim column here with DEL, and we're seeing it's gone. So now we can continue working with our insurance 2 data set. Okay, so as before, I'm going to set up my independent attributes again. Here we have our X. All right, so now I'm going to set up my independent variables here for my formula and my dependent variable. Independent variables is everything minus the last column here. This is why it says -1 here. And then my Y, my dependent variable, is column number 6, because remember 0, 1, 2, 3, 4, 5, 6. So I want to build a NumPy array with these, with all of the rows here. That's all 1338 rows, right? And I want to build this on axis equals 1. And then the last piece of my definition is that for my optimizer, I am choosing to include in my optimizer all of my input variables in columns 1 through 5, in columns 0 through 5. So now I can set up my OLS regressor, and I'm going to use my stats models OLS again. And this is a little bit strangely formulated here. My endogenous response variable is always the Y variable, that's the dependent variable, and my exogenous response variable is the number of the regressors and is the type of regressors, and we have defined those up here. Okay, so that's just a fancy way of saying Y and the array for our X opt here. Okay, so now we can print our summary, right? Good. So here we're seeing again our coefficients, right? We're seeing that the numbers haven't changed very much for our X1, which is age, and the ones that we are already familiar with. However, our constant all of a sudden has gotten really, really small. Do you see the E here? That is very, very small. Interesting. Okay, and at the same time, see what our R squared value is, and we're seeing that the R squared value has increased dramatically. It has increased from, well, first we had 8.9% with just the age variable, then we had 12% with all the initially numeric variables, and now look, we have 75%. That is a really good result. So with all variables combined, we can achieve an R squared value in our multiple regression of 75%. Can we do better? So let's see, let's see, what do we have here? Let's find out how valuable sex really is in predicting. Maybe it is, maybe it isn't, right? Let's see if we can do better than the 75%. That's what we're trying to beat. So we're going to remove sex as column number 1. So our X opt is being set up as 0, 2, 3, 4, and 5. We've removed sex. We're going to set up our regressor yet again, right? And we're going to print the summary. And, oh, well, okay. So removing sex removes, yeah. So sex was really important because you see how our value has changed, our R squared value has changed from 75% to 66%. Okay, so that was probably not it. Okay, so what if children actually has a negative effect on sex, and we are going to see our R squared increase if we remove children? Let's try that. Why not? I had a very small R2 before, so let's see. Oh, so we're seeing here the R squared value if we remove children goes down to 62% from the 66% here. So we still haven't beat our 75%. All right, so let's see what is next. So what if we remove BMI? We'll add sex back in and then see what happens. Let's see. So we have 0, 1, that's sex. BMI is 2, so we have that, and then all the others. So maybe BMI is not fantastic for, oh, okay, so if we remove BMI, we're at 75% again. Okay, well, that's actually good news, you know, because if we keep all the attributes, but we remove BMI, that means, and our R squared value is at 75% because it hasn't changed from the very, very beginning, right? Then we just saved ourselves some processing power. That's really important because when you have a really big data set and you have hundreds of thousands of attributes, just reducing the number of calculations, that can come in very handy. So, okay, removing BMI was actually a pretty good idea. Very good. So now that we know that removing BMI really didn't do anything to our highest R squared value, let's see if we can maybe save ourselves a little bit more processing power and get rid of region as well. Let's see what that does. Oh, wow, look at this. So if we remove BMI and region, then our R squared value drops down to 12%. What does that tell us about region? What do you think? What does it tell us about region? We definitely want to keep it, right? So, all right, let's remove smoker instead. All right, so we are using 0, that's age, 1, 6, 3, and 5. We know that 2 is BMI and 4 is smoking status. Remember, 5 was region. We didn't want to remove that because that really dropped our R squared value. So let's see. Okay, so our R squared value dropped just slightly to 74.7. Okay, well, let's see. That really isn't much of a difference between 74.7 and 75. Okay, so here we have to talk about trade-offs, right? We have now eliminated 2 attributes. That is, well, it's 1338 rows times 2, so roughly 2600 values, right, that we didn't have to process. And we haven't really lost much in terms of our R squared, in terms of our, quality of our model. So I would suggest, and the results show us that as well, that you don't have to use all of the attributes in order to have a pretty good prediction quality, right? You can use, as we're doing here, we can use 4 out of 6 and still get an almost optimal prediction quality, but we can save ourselves a lot of processing. And this is always your trade-off in data mining and in big data, namely that you don't want to process the data that you don't have to. And here we have seen that this is a pretty good proof of that. All right, we found the optimal mix of attributes here. And we're getting the biggest bang for the buck because we're saving ourselves some processing, right? And we're still getting some really good r-squared values. And should we stop here? No, we can't stop here, because let's go back to our original goal. Our original goal was we wanted to find a function that allows us to predict the future value of the charges attribute, which means we wanted to be able to use our independent attributes to calculate our y, our dependent attribute. But we already know all of our y's, all our y values. So we really have just two options here, right? We need more independent attribute values, but we're going to get them. So we might have to invent them maybe, or we can remove some of the y values, some of the charges, and then we can apply the formula that we have built to the independent attributes for those charges values that we have removed, and then see what the result is, and then we can compare the calculation outcome with the values that we have removed, and then we can see how close they are. That is actually what we're going to do. And that is what we're going to be doing from here on out in our step into machine learning. What this is called is building test data sets and training data sets. We use training data sets in order to train our function, that is to build our function, and then we use a test data set from which we have removed the dependent variable in order to predict that dependent variable, and then we're going to compare that output to the removed values. So predictions versus the actual removed values. Okay, so how do we do that? Let's walk through that. We're going to use what's called a train test split function from scikit-learn for this, and we're going to build a separate xtrain and an xtest frame, and a ytrain and a ytest frame. So here we're going to use the train test split, and we're going to build xtrain, which will have the training data set. They're usually bigger. The xtest, which is typically a smaller test data set. We're going to build the ytrain data set, which is the dependent variables, that's the charges that are related to xtrain, and ytest, which are the currently still the variables, the dependent variables that are related to xtest. And then we're going to use our xopt for that, and our y, and we're going to use our test size, which is going to be 0.2, which means that we're going to use 20% of our data as the test data set, and we're going to use 80% of the data as our training data set. Okay, so, and that gives us 1070 rows in our training data set, in our xtrain, right? And gives us 268 in our xtest, and we would have exactly the same values in our ytrain and our ytest sets. So now we can use our regression formula, and here we are going to just say we're going to import our linear regression from our scikit-learn, and we're going to set our regressor to linear regression, and then we're going to fit that. You can also do that in one step with the xtrain and the ytrain. And then we're going to print what is called the model accuracy score, which means the accuracy score for our model, and we're going to round that as a percentage. Okay, a percentage with 2 digits here. So our model accuracy score, if we build it on the basis of our xtrain, our training data set, which is 80%, is 73.43%. That is very close, remember? Very close to this here, right? Good. That looks good. So 73.43%. So basically that is the R squared value expressed as a percentage and rounded to 2 decimals. So very close, right? So now we're going to, that we have the regressor here, we're going to apply this regressor, this model that we have built on the basis of the training data set to our x-test, to our test data, and then our outcome will be our predictions, right? Our calculated value. So we're going to call this y-pred because we can. So what we're seeing here is the first 10 values, just printing here 0 through 10, the first 11 values of our predictors. Great. Okay, so now we can take these numbers here and compare them to the actual numbers that are associated, that we know, because we're cheating, right? That we know are associated with x-test, and that's our y-test, right? So we can now say we're going to build a data frame of our y-pred versus our y-test, the actual values that we have stored in our y-test that we haven't used, right? So here we go. Here's our prediction, the outcome from our prediction. You see this is up here, right? And then the actual values of our y-test are here. Okay, so there we go. All right, so the y-pred data are a little bit different here at times, right? From the y-test data, but they're also, in some cases, they're pretty close. Okay, so this is why the accuracy is at around 73% here, which we had calculated for the up, right? Not super great, but certainly not super bad, right? And certainly better than 8.9 or 12%. All right, so now you've just learned how to use simple regression and a training test split to calculate and predict numeric output. See here the prediction versus the actuals. Pretty cool, huh? And regression is, of course, it's a mathematical tool. It calculates, right? But what if we don't want the output to be numeric? What if we want the output to be categorical, right? So, for example, what if we want to use a student's grades to predict whether they will pass or fail a class at the end of the semester, right? Or what if we want to use a soccer team's past number of goals in a tournament to predict whether they will win or lose the World Cup, right? Or see if body weight or calorie intake or fat intake or age have any influence on the probability of having a heart attack, right? So all of these outcomes that I just mentioned are always yes, no, 1, 0, valid or not valid, and that kind of thing. And remember that insurance data set that where we had that additional dimension that we deleted. And that was up here. And that's going to come in handy now, because now we're going to talk not about predicting numeric value, we're going to talk about predicting a categorical value. And for that, we are going to predict our insurance claim. Insurance claim, remember, showed us whether insurance was actually claimed and granted, or whether insurance claim was claimed and not granted, right? Okay, so that's what we are going to predict now, whether the company should grant the insurance claim or not. In order to do that, though, we need a different type of regression. That type of regression that will allow us to predict a categorical output as the result of our calculations is called logistic regression. Logistic regression can help us predict whether, for example, a soccer team is going to win the World Cup based on scores from past tournaments, or whether a student is going to pass or fail a class based on the grades that they have earned so far in that class, that kind of thing. How exactly logistic regression works and how the logistic function works, that is, the log odds function and the log odds logarithm that it applies to the outcome of a multiple regression, that is what you will learn in this video. So how do we work with logistic regression? Well, first we're going to need our entire data set, which I've already loaded here with the insurance claim column. And then we're going to check our data set against the 3 rules of logistic regression. Remember, the dependent variable should be dichotomous. Well, that's already true here because we have ones and zeros in insurance claim, which is our new dependent variable. Good. There should be no outliers in the data. Well, we kind of know that the outliers, that we kind of have outliers, right? So the data set is not as clean as we would want it to be, but in the interest of time, we're going to work with what we have. And then rule number 3, there should be no high correlations among the predictors, among the X variables, right? So that's called multicollinearity, because if we have high correlations among the X variables, that tells us that the X variables are more related to one another than to the Y variable, to the output variable, or to the class attribute, whatever you want to call it, the dependent attribute, right? So let's check that now. Okay, the first thing we're going to need to do is set up a correlation table and between all of the attributes in our insurance tree, this data frame here. I'm going to add numeric only true here because the correlation function will work better. So now let's see, here's insurance claim. And what number do we have to beat in order to see if we have multicollinearity in the data set? The highest correlation here is insurance claim and BMI. So that's 38% or 0.38. Yes. So now let's see if we have any correlations that are higher than 0.38 here among these attributes. So I'm going to run through these real quick. Doesn't look like it, does it? Oh, look at that. So here we have smoker and charges. So this tells me that we are failing the test for multicollinearity and that the smoker attribute here is very, very highly connected to charges. And there you go. You can type the smoker variable into this field here, right? That's your turn for that. But we can even visualize these correlations. You know, we don't have to. It was pretty cumbersome to look at all the numbers. And let's see how we can use a graphic in order to display the numbers better. So here we're using the Seaborn package, and we're going to set up a heat map from the Seaborn package on our data here. Okay, so, and what we're seeing here is we know that age to age is related with a 1.0. That shows us the 1.0 is the dark purple. So anything that's purple is strongly related. We know that anything that's very dark green is strongly negatively related. We saw that already. And we're seeing right away here that charges is light purple, so kind of around this area here, and that exactly is our value of the 0.78 here, right? Okay, so what are we going to do about this? So ideally, we could remove the smoker variable from our data set in order to not run into the multicollinearity issue. On the other hand, we saw that our smoker variable is possibly very important for our data set, so I'm choosing to leave it in and instead work with a data set that fulfills only 2 out of the 3 requirements for logistic regression. As long as we know why we're doing what we're doing, we are always fine. All right, so now I'm going to, as before, set up my training and my test data set. Here I'm going to use a different strategy. I'm going to allocate all rows up to row 1000 to my training data set. I'm going to allocate rows 1000 to 1300 to my test data set, and I'm going to stick the remaining 38 records into a checked data set just in case I need it. So this is a different way of splitting the data set. Previously, we've done it with an 80-20 percentage. Here, we're doing it by row numbers. Okay, so the next thing I want to see is I'm going to add a code line here. What is actually inside my training data set? So let's see. 1000 rows, 8 columns. Okay, good. That's exactly what I wanted to see in there. Good. Life's good. Okay, so the next thing we're going to do is to separate the Y's from the X's, right? Or the labels from the features, or the dependent attribute from the independent attributes. We've done that before as well. So I'm going to build a train Y, train X, test Y, and text X data frame here, and or an array, and I'm going to use for my training Y, I'm going to use just the insurance claim of DF train, just like for my test Y, I'm going to use just the insurance claim from my test. And then for my training X array, I'm going to use everything else in DF train. Here you see the only thing I'm dropping is insurance claim, right? Same thing for test X. So let's see what train X looks like now. All right. Okay, so we have values. Looks a bit scary, but you know what? All the data is there. That's what we need. So the next thing we want to talk about is, for going forward, we want to be sure that the input data that we send into a model really is what we call normalized, meaning that all the values are on the same scale. How do we achieve that? There's different ways of going about that. Here is one of them. To normalize the data, here we are going to subtract the means of the data points from the actual values and then divide them by the standard deviation. And that will allow us to put all the values on a scale between 0 and 1. So that's what we're doing right now. So now we have our train X and our test X already calculated. Now we can build the model, right? We have our data prepared, we have our training sets and our test sets, and all our data is normalized. To build our model, we are going to import logistic regression, and then all we have to do is fit our model on train X and train Y. There you go. And that doesn't give us anything. It just tells us, well, we're doing a logistic regression. Okay, fine. But what is more important to us is, well, we're going to want to check our model score, our accuracy of our model. Is our model actually being accurate in our training data set? And we're seeing we have an accuracy here based on test X and test Y, applying the model to test X and test Y of 86%. So that's a pretty impressive score here. So now let's take a look at the predictions in detail. So we're going to use model.predict, and we're going to predict on the X variables because we want to predict our Y, right? And so these are our predictions now on our test data set on those 300 values that we've stuck in there. So if you were to count, these would be 300 ones or zeros. And that's the calculated output. So now we're going to do the same thing that we did before, where we put into a data frame the real versus model, namely the prediction and the actual test values, right? And then we can see if the predictions are close to the original, and if that 86% accuracy is actually 86%, if we're kind of getting the gut feel that, yeah, this looks about right. What we're seeing here is that it's pretty accurate, right? Our predictions versus the original, our test Y, right? We have a couple of differences here for data point 11 here, 15, but really not that much. All right, so now it's going to be your turn. I'm going to ask you to create a subset of the adult data set with just the numeric variables and to use the logistic regression to predict the sex of someone based on all the numeric input. All right, have fun. And this concludes our walkthrough of the linear modeling workbook. Looking forward to seeing you again in another walkthrough. Bye.